Estimating mutual information from samples of a joint distribution is a notoriously challenging problem in both science and engineering. To address this, a hybrid method is proposed, combining the strengths of generative and discriminative approaches to mitigate their respective limitations. This unified approach yields a tighter bound on the information, achieved through reduced variance. A novel generative method, predictive quantization, (PQ), is introduced, which can be seamlessly integrated with discriminative estimators, incurring minimal computational overhead. The efficacy of these methods is demonstrated through empirical testing on challenging tasks, involving correlated high-dimensional Gaussian distributions and a stochastic process. Results show that the hybrid methods consistently outperform their discriminative counterparts in estimating mutual information, underscoring the potential of this unified approach in overcoming the limitations of traditional methods. By leveraging the strengths of both generative and discriminative techniques, this hybrid method provides a more accurate and robust means of estimating mutual information, with significant implications for various applications in science and engineering. Mutual information estimation is a crucial task in machine learning, typically done by maximizing the ratio of mutual information to the variational gap. The variational gap is the Kullback-Leibler divergence between the joint distribution and its variational approximation. Two categories of approaches have been proposed: generative and discriminative methods. The mutual information between two random variables x and y is defined as the Kullback-Leibler divergence between their joint probability density and the product of their marginal distributions. To overcome the limitation of unknown densities, a variational distribution q, x, y, is introduced to obtain a lower bound on the mutual information. This lower bound, known as the variational information, is the expectation of the log ratio of the variational distribution to the product of the marginal distributions. The key challenge is finding a flexible variational family that can accurately approximate the joint distribution. Previous work identified two approaches: generative and discriminative methods. Generative approaches model the components of the variational information using learnable normalized densities, while discriminative approaches directly model the entire ratio. However, both have limitations. Discriminative approaches can suffer from bias or high variance, especially for large values of mutual information. Generative approaches require access to flexible parameterized distributions, which can be hard to attain or expensive to optimize, especially for high-dimensional x and y. To address these limitations, the authors propose predictive quantization, (PQ), a simple generative method that can improve recently proposed discriminative estimators. PQ uses a quantization function q, x, to obtain proposals closer to the target joint distribution than the product of the marginals, effectively reducing the variance of popular discriminative estimators and resulting in a tighter estimate of the variational bound. The effectiveness of hybrid mutual information estimation is discussed, focusing on the additive decomposition of terms in equation 2 and equation 6. A parametrization for the joint probability distribution q, x, y allows for the derivation of popular mutual information estimators and the proposal of new hybrid estimators. The discussion revolves around energy-based models and their normalization constant, addressed by computing a Monte Carlo estimate. A reparameterization of the energy to obtain a valid density leads to a general bound that includes both generative and discriminative components, visualized in Figure 2 as the decomposition of total information into a lower bound and respective variational gap. The paper focuses on the effectiveness of hybrid mutual information estimation, specifically examining the two components of equation 6. The first component compares the value of the critic for samples from the true joint to samples from the proposal, represented by the Donsker-Varadon representation of the variational gap of the proposal. This inequality is tight when the family of transformed densities F contains at least a constant function k, which is a reasonable assumption given the flexibility of critics modeled using function approximators. The discriminative approach is discussed, where r, x, y, equals p, x, p, y, causes I r, x, y, to vanish from equation 6, allowing for great flexibility in modeling density ratios directly with neural network critics. However, its efficacy heavily depends on bias-variance trade-offs of the chosen approximation to evaluate the normalization constant. The paper also discusses the generative approach, where f, x, y, equals k, causing the second term of equation, 6, to vanish. This setting requires access to a flexible family of distributions with known or approximate densities, highlighting popular modeling choices for joint and conditional proposals, including transforming simple densities using normalizing flows. The authors of the research paper address the limitations of existing generative approaches to mutual information estimation, which often face a trade-off between flexibility and computational costs, thereby limiting their effectiveness in high-dimensional settings. To overcome these challenges, they propose a hybrid method that combines the advantages of both generative and non-generative approaches. This hybrid method involves considering proposals R, X, Y that lower the variance for the estimates of KLF, P, X, Y, R, X, Y, and refining the proposal using a flexible F, X, Y, such as a neural network. This approach allows for the inclusion of flexible density estimators, which can correct for any lack of flexibility in the proposal. The authors then outline an iterative method for optimizing the proposal and the ratio between the proposal and the joint distribution. They define a simple family of proposals RQ that are guaranteed to lie closer to the joint distribution P, X, Y than the product of marginals, while yielding simple and efficient computation of IR, X, Y. They introduce predictive quantization, a joint distribution RQ, X, Y, that factorizes as P, X, P, Y, Q, X, where Q maps to a discrete quantization X equals Q, X. This proposal allows for tractable estimation of IR, X, Y, and has three key advantages. It enables good estimates of H, X, for reasonable numbers of quantization intervals. It allows for easy sampling of RQ, X, Y, and it satisfies KL, P, X, Y, RQ, X, Y, less than KL, P, X, Y, P, X, P, Y, for any Q such that I, Y, Q, X, greater than 0. The authors provide an algorithm for hybrid mutual information estimation using predictive quantization, which involves iteratively optimizing the proposal and the ratio between the proposal and the joint distribution. They highlight the importance of choosing Q, X, such that I, Y, X, is large, causing RQ, X, Y, to be closer to the optimal proposal. Hybrid mutual information estimation achieves improved effectiveness by integrating predictive quantization, or PQ, with discriminative estimators. This approach involves sampling batches conditioned on one quantized value, rendering the shuffling operation equivalent to sampling from the marginal distribution. Previous works have been limited by exponential variance scaling in discriminative estimators. To address this, the authors propose a hybrid approach that combines the strengths of both methods. They evaluate their approach through empirical experiments on tasks with known true mutual information, including a correlated mixture of normal distributions and a discrete time particle simulation. The experiments compare different discriminative estimators with and without the PQ component, showcasing the benefits of the hybrid approach. By integrating PQ, the authors reduce variance and improve estimation accuracy. The results demonstrate that the hybrid approach outperforms standalone discriminative estimators, highlighting the potential of this method for accurate mutual information estimation. In these experiments, the authors provide a comprehensive analysis of the hybrid approach's performance, offering insights into its advantages and limitations. By addressing the limitations of previous works, the authors contribute to the development of more effective mutual information estimation methods. The effectiveness of hybrid mutual information estimation is discussed, focusing on the combination of generative and discriminative estimators. Various generative approaches are overviewed, including BA, DO, GM, and the author's proposal, PQ. The benefits of hybrid estimators are highlighted, improving upon their discriminative counterparts. Figures 3a and 3b demonstrate improved mutual information estimates and reduced bias and variance with the addition of a generative component. Applications to discrete-time multi-particle simulation are emphasized, highlighting the importance of stochastic processes in scientific discovery. This research introduces a hybrid approach for estimating mutual information, combining the strengths of discriminative and generative methods. The proposed predictive quantization (PQ) method, a nonparametric generative approach, enhances discriminative estimators, yielding improved mutual information estimates with lower variances. Existing discriminative and generative approaches have limitations, which the hybrid model addresses by leveraging the strengths of both paradigms. To evaluate the effectiveness of this hybrid approach, a particle dataset is simulated using discrete time overdamped Langevin dynamics, allowing for the computation of entropy and conditional entropy of the transition distribution, and thus, mutual information between consecutive time steps. The dataset is modified to introduce spurious correlations and increase dimensionality, making it a challenging test case for mutual information estimation. Temporal independent component analysis (TICA) is applied to project the 30-dimensional feature space onto 10 principal components, ensuring particles with high temporal correlation have similar representations. Nearest neighbors clustering is then used to obtain Q, X, for all particles and time steps, resulting in a proposal distribution RQ, xt plus 1, xt, that captures temporal information and improves I, xt, Q, xt plus 1. Results show that including a generative component yields improved mutual information estimates for tested estimators. A bias-variance trade-off analysis reveals that increasing the number of quantization intervals Q, X, reduces variance for most estimators, except for info-NCEBASED estimators, which are characterized by low variance and high bias. The increase in variance for info-NCE estimators is attributed to the estimation of the PQ generative component. The hybrid approach and PQ have the potential to improve mutual information estimation tasks. While the proposed method introduces additional complexity due to the interplay between the two components, it is believed that simple proposals could be used together with discriminative models to maximize information between learned representations in future work. Mutual information estimation is a fundamental concept in information theory, quantifying the amount of information one random variable contains about another. This concept is crucial for understanding relationships between variables in complex systems. To accurately estimate mutual information, various techniques and methodologies have been developed. One approach is the nonparametric estimation method, which avoids assumptions about the underlying probability distribution. This method utilizes kernel density estimation, nearest neighbors, and other techniques to approximate the mutual information. Another approach is the parametric method, which assumes a specific probability distribution, such as Gaussian or exponential, and employs maximum likelihood estimation. The nearest neighbors algorithm is a popular nonparametric method, which estimates the mutual information by computing the average distance between data points in high-dimensional space. The binning method, on the other hand, discretizes the data into bins and calculates the mutual information using the histogram-based approach. Bayesian estimation methods, such as variational inference and Markov chain Monte Carlo, have also been applied to mutual information estimation. These methods provide a probabilistic framework for estimating the mutual information, incorporating prior knowledge and uncertainty. The choice of estimation method depends on the specific problem and data characteristics. For instance, nonparametric methods are suitable for high-dimensional data or when the underlying distribution is unknown, while parametric methods are more efficient when the distribution is well defined. Recent advances in machine learning and deep learning have also been applied to mutual information estimation, such as neural estimators and deep learning-based methods. These approaches leverage the powerful representation capabilities of neural networks to estimate mutual information in complex systems. Despite the progress, mutual information estimation remains a challenging task, particularly in high-dimensional spaces or with limited data. Future work includes developing more accurate and efficient estimation methods, as well as exploring new applications of mutual information in fields such as neuroscience, genetics, and finance. The 7th International Conference on Learning Representations introduced a novel approach to learning deep representations through mutual information estimation and maximization. This concept has been explored in various studies, including the work of Ho, Jane, and Abiel on denoising diffusion probabilistic models, which demonstrated the effectiveness of hybrid mutual information estimation for enhancing model performance. Hyv Diaris's Aronen's research on score matching and independent component analysis further underscored the potential of mutual information in machine learning. The use of mutual information as a measure of statistical independence between variables can significantly improve the quality of learned representations. Kingma's contributions to stochastic optimization, auto-encoding variational Bayes, and improving variational inference with inverse autoregressive flow have also played a crucial role in advancing the field. These methods have shown promising results in learning complex distributions and improving the efficiency of variational inference algorithms. The hybrid mutual information estimation approach combines different techniques to leverage their strengths. By integrating multiple methods, such as score matching, denoising autoencoders, and variational inference, researchers can create more robust and efficient models for learning deep representations. This approach is particularly beneficial for handling high-dimensional data and complex distributions, where traditional methods often struggle. The ability to accurately estimate and maximize mutual information enables models to capture intricate patterns and relationships within the data, leading to improved performance in various machine learning tasks. While the hybrid mutual information estimation approach has shown promising results, there are still limitations and areas for future work. For instance, the choice of specific techniques and hyperparameters can significantly impact model performance, and developing more efficient and scalable algorithms remains an ongoing challenge. In conclusion, the hybrid mutual information estimation approach offers a powerful tool for learning deep representations in machine learning. By combining various techniques and leveraging their strengths, researchers can create more effective models capable of handling complex data distributions. As research continues to evolve, refining these methods and addressing remaining challenges will be crucial for advancing the field. The authors delve into the efficacy of hybrid mutual information estimation methods within the realm of contrastive representation learning. They cite pertinent prior work, such as sliced score matching, Song et al. 2020, and decomposed mutual information estimation, Sordoni et al. 2021, which have demonstrated the scalability and efficacy of hybrid approaches in estimating mutual information. The information bottleneck method, Tishby et al. 2000, is also referenced, providing a framework for understanding the trade-off between compression and prediction in representation learning. Additionally, the authors mention contrastive predictive coding, Van den Oort et al. 2018, a method that leverages mutual information to learn representations by predicting future states in a sequence. Furthermore, they reference VAEBM, Xiao et al. 2021, a symbiotic approach that combines variational autoencoders and energy-based models to learn representations. They also cite Barlow twins, Zibontar et al. 2021, a self-supervised learning method that reduces redundancy in representation learning. The author's discussion underscores the importance of hybrid mutual information estimation methods in contrastive representation learning, which can effectively capture complex dependencies between variables. By combining multiple estimation methods, these hybrid approaches can provide more accurate and robust estimates of mutual information, leading to better representation learning outcomes. In this research, we adopt specific notation and conventions for random variables, expectations, Kullback-Leibler divergence, mutual information, and entropy. We focus on discriminative mutual information estimators, including NWJ, MINE, InfoNCE, and JS, each characterized by its objective function. The objectives are designed to optimize the critic by minimizing or maximizing functions related to mutual information. NWJ's objective function, for instance, involves minimizing the Kullback-Leibler divergence between the joint distribution and the product of marginals. In contrast, MINE's objective maximizes the mutual information between the input and output variables, using a neural network-based critic to estimate the density ratio. InfoNCE, on the other hand, employs a critic that learns to distinguish between positive and negative samples, with its objective function being the logarithmic loss. JS, a variant of InfoNCE, uses a critic that learns to distinguish between positive and negative samples, but with a different logarithmic loss function. Each estimator's formulation highlights distinct approaches to optimizing the critic for mutual information estimation. The parametrized critic architectures for these estimators are also described, detailing the specific neural network designs and optimization strategies employed. By examining these objective functions and critic architectures, we can gain insights into the strengths and limitations of each estimator, ultimately informing the development of more effective mutual information estimation techniques. The effectiveness of hybrid mutual information estimation is discussed, focusing on two specific methods: NWJ plus info NCE and SMILE. For NWJ plus info NCE, an interpolation of the baseline is used, combining NWJ and info NCE with a parameter alpha set to 0.5. SMILE estimates mutual information equivalently to MINE with value clipping inside the exponential. The parameters are updated using the same objective as JS. The section includes proofs, detailing how the mutual information I, X, Y, can be composed from IR, X, Y, and KL, P, X, Y, R, X, Y, and discussing the variance of the normalization constant. The paper presents an improved bound for hybrid mutual information estimation, considering a set of attainable critics f and incorporating a constant function fk to ensure the lower bound is at least as good as a fully generative approach. The improved bound is formalized as an equation involving the mutual information IR, X, Y, and the Kullback-Leibler divergence between the estimated and true distributions. To experimentally validate this bound, the authors employ various models and datasets, including generative and discriminative models with specific architectures, and the normal mixture dataset. They also explore a discrete time multi-particle simulation task, utilizing a log-density mixture of normal distributions as an energy function. The results of this simulation demonstrate the efficacy of the proposed bound. Furthermore, the paper provides additional experimental results, illustrating the impact of increasing the number of samples on the normalization constant for several mutual information estimators. These results highlight the importance of considering the improved bound in hybrid mutual information estimation. The efficacy of hybrid mutual information estimation is further elucidated through a visualization of the 2D energy U, X, and a portion of a simulated trajectory for one particle used to generate the dataset, as depicted in Figure 5. This visualization provides insight into the underlying structure of the energy landscape. The impact of increasing the number of negative samples on mutual information estimation is investigated in Figure 6, where the performance of various estimators is compared for a fixed batch size of 64. The results indicate that the MINE estimator initially overestimates mutual information with fewer than 4 negative samples, but switches to underestimation with more than 4 negative samples. In contrast, the NWJ and JS estimators exhibit more consistent behavior, with the NWJ estimator demonstrating lower bias and variance across the range of negative samples. The generative estimator, which serves as a baseline, performs poorly, highlighting the importance of incorporating negative samples in mutual information estimation. The PQ estimator, a hybrid approach, exhibits competitive performance, but with higher variance than the NWJ estimator. These findings underscore the significance of carefully selecting the number of negative samples and the choice of estimator in mutual information estimation tasks. Overall, this analysis highlights the trade-offs between different estimators and the importance of considering the number of negative samples in achieving accurate mutual information estimation.